Hello. Uh, Today is the last class of the course, and the goal is going to be to derive the Schrödinger equation as an example of an entropic dynamics. In the previous chapter, when we were talking as a prelude to dynamics, we managed to get equations that were very much like the Schrödinger equation, but we had no idea of what time was, and neither did we have a good idea of what the Hamiltonian might be. We knew that it had to be Hermitian, but we had no idea of what were the allowed forms for the Hamiltonian. What we want to do today is we want to continue working on entropic dynamics. Entropic dynamics answered some of those questions that had been lingering. Namely, now we have a pretty decent idea of what we mean by time. It's a tool that allows us to keep track of successive updates of the probability distributions. And we even have a decent idea of what the Hamiltonian might look like, because we know a little bit about what the equation of evolution for the probability, the continuity equation, should be. So let's review what those, the tools that we have at hand and proceed further. So here we go. So last class, we had seen that the basic equation of evolution was an equation that took this form, where we introduce this parameter t that allows us to go from one instant to the next, and the transition probability, which was obtained using the method of maximum entropy. This is where the entropic dynamics comes in, is given in the form of a Gaussian. And then here we have delta xa, delta t minus va, delta xb, delta t minus vb, where I remind you the uppercase indices are indices in configuration space. So this is A or B. That denote what the particle is. A tells you coordinate x, y, z, and tells you which particle we're talking about. So the index A stands for both n and A at the same time. The tensor MAV is the mass tensor. It's just a diagonal tensor, and n prime delta AB. It's a diagonal tensor in these three n dimensions, where the diagonal elements are given by the mass of the particle. At this point, we do not know that this constant m is going to be mass. We will know that once we get to the Schrödinger equation and we see where it shows up. What else? Eta is just a constant, of no particular significance, except for the fact that it's already telling us that you have a whole family of transition probabilities that seem to imply eventually more or less the same Schrödinger equation. It's a freedom we have there. Now, this basic dynamical equation can be written in differential form. You can write this as a continuity equation. Rho V A. So on the right hand side we have a divergence in configuration space in 3n dimensions. And we saw that this is what I meant by saying entropic dynamics gives you a fairly decent idea of what you actually mean by the parameter t. It's something that allows you to iterate probabilistic changes. And we have a pretty decent idea of what the equation of evolution is going to be. There you have it. It's this continuity equation where this velocity a is, which appears up here in the transition probability, is the expected the expected step divided by delta t. And further, this is written in terms of the constraints. This is where the constraints come in. What we have here with this tensor with indices upstairs is the inverse of the mass tensor. So this is, if this were just for one particle, what you would read here is 1 over m. So mv is equal to that gradient of phi minus a. And of course, the notation here has been chosen so that it starts resembling the traditional theories of physics. In particular, an equation such as this, a phi minus a is exactly the kind of equation that you get in Hamilton, in the classical Hamilton-Jacobi theory. So this really starts resembling physics. Here we have the two constraints that we have imposed. The quantity phi came from one of the constraints, the drift constraint, and this is what we're going to see shows up as the phase of the wave function. And the other constant that here I've called with r, this is the constraint that comes from the vector potential. So it accounts for electromagnetic interactions with an external field. Very good. What else did we do the last time? Yes. Then we said, look, this equation here can be rewritten in a particularly clever form. Write the equation as dt rho is equal to the functional derivative of a functional h d phi, and this is at x, and this is x. And we said something like, look, what we have here is that minus the divergence of rho, and then here I'm going to write the VA, which includes the phi, the capital phi. This is the equation we want to find, we want to solve to find what the appropriate H tilde is. Now this equation here, let me rewrite it in a cleverer way using our expression for the velocity. VA is given by this expression. So this equation here, I can write it as minus dA rho m a b d b phi minus a b equals d phi x. This equation here is particularly simple. We can integrate it easily. If you see here these derivatives, dA, dv, these are derivatives with respect to x, while this is a functional derivative with respect to phi. So this equation is very much analogous to something like df dx I is equal to a matrix, I don't know, call it M, I, J, X, J, something like that. That equation is trivial to solve. You just get that F has to be Xi, Mij, Xj plus some constant, 1/2. So being a trivial linear equation, we can solve that, and the corresponding h is going to be something that is a function of rho and of phi, and it's going to involve an integral, and it's going to involve rho, and then we have here the inverse mass tensor d a phi minus a the b phi minus ab plus an integration constant. So we showed last class that if you take the functional derivative of h with respect to phi, then of course this f, this integration constant, does not contain phi. It drops out. You take just the derivative of this phi and of that phi, integrate one's phi parts, and you get exactly that equation. So the solution here is very clear. Very good. So what are the state of things here? Well, the state of things here is that we have basically 1/2 of quantum mechanics at this stage, or at least we have a dynamics of probabilities that seems reasonable. However, we have a problem. The problem is that we have this variable phi, and we managed to have an equation here of evolution for rho. But if you actually, well, when you look at such an equation, you say, yes, we have a degree of freedom here, rho, and nothing else. There is no second degree of freedom. The phi's that appear here, phi, is just an external field, very much like the vector potential. So these are not degrees of freedom. They're just fixed. So what we are going to get, if we try to figure out what this equation of motion looks like, is just a diffusion problem. This entropic dynamics is just a diffusion. It's just an evolution of the probabilities in a certain direction. It's not even a diffusion, really, because the probabilities evolve with very nicely defined velocities. So this entropic dynamics is just a flow. How do we solve this? Well, the way to address this problem is to recognize that at this stage in the game, if I give you the constraints, I can tell you how the probability, well, from this equation is particularly clear. I give you the constraints implicit in the V that appears here, and this tells you how you evolve to the next instant. If I want to have a fully dynamical theory also for these potentials here, what I would like to be able to do is say, look, once phi tells rho how to evolve to the next instant, I would like rho to tell phi how to itself evolve to the next instant. In this way, we make phi dynamical. Solution. We need to make phi, the constraint, part of the dynamics. What this means is that phi affects rho, and then we need to have a rule that tells us how rho itself affects phi. We need a law of evolution for the constraints. The law of evolution for the probabilities is clear. It has to be some kind of entropic updating. That's the only consistent way. The only way to do it that is consistent with the principles of entropic inference. The update of rho has to be done with maximum entropy, and this requires constraints. But what is the rule for updating the constraints themselves? At this point, it is that we're going to use symmetries. So rho affects phi, but how? So we're gonna, for this part of the game, we're going to impose symmetries. In particular, we're going to figure out that what we want is a time evolution that preserves some symplectic structure, a flow, let me write it like this, a flow along a particular vector field that preserves a symplectic structure, and a flow along a vector field that preserves a metric structure. So our next goal is going to be to construct a symplectic form and to construct a metric tensor. What we're going to be doing is precisely what we did in the last few classes, except that there we were doing it for the finite dimensional case. Now we're doing it for an infinite dimensional case. You see, you have this rho depends on x, so you have an infinite number of degrees of freedom, one at each point x on the configuration space. So we're going to need to have a clever notation to do this in a more or less efficient way. But apart from that, the mathematics is going to be exactly the same that we did before. So let us proceed to see how we handle that. So the notation first. Earlier we had been dealing with a simplex. And the simplex was, if you had an n-sided die, the simplex was n-1 dimensional. This was the set of probabilities such that the probabilities were normalized. Then we actually invented something that was very useful. We said, look, this normalization constraint is going to be a problem because it obscures the spherical symmetry of the simplex if we just eliminate one of those variables. So it is a good idea to embed this into a space that has one dimension higher, and we called it S+1. We embed it in a larger space. These are these probabilities or relative probabilities that are positive but without any constraint. And then we said it's a good idea to figure out the cotangent bundles associated to these guys. One of them is the cotangent bundle associated to the simplex, which is the one that we were interested in. And the other one was the cotangent bundle associated to the embedding space. This guy here has n-1 dimensions. And let's see, n-1 dimensions. You can see it from the simplex. And because we're doing the cotangent spaces, you double it. So, and this guy here has n dimensions for the embedding space, and you double it to n. So what we want to do now is the analog of this equation for our probabilities. The infinite dimensional simplex we're going to call it P. It's a space of probabilities. It is the space of all row x's that are positive and that are normalized. And we're going to use the notation that was useful from before to call this rho equals 1. And we're going to want to embed this space because of the normalization constraint being such a pain in all of these calculations. We want to consider a space that has one dimension more. And this is going to just be the space of row x's that are positive. And associated to these guys, we're going to have the cotangent bundle of P and the cotangent bundle of, P plus 1. So this guy here is going to have 3n infinity minus 1 dimensions, and then this doubles it. And this guy here has 3n infinity, and then when you do the cotangent bundle, you double it. So this is one of the reasons why I've been using this plus 1 as notation for the embedding space, because 3n infinity minus 1 actually is exactly the same thing as 3n infinity, right? What's infinity plus or minus 1? Still infinity. So I just want to say by this plus 1 that, of course, we're not imposing that constraint. So we need a better notation to do all of these guys here. And so the notation that we're going to use is we're going to say a point in this cotangent, in the embedding cotangent space, is going to be described by coordinates. And we're using a composite coordinate. Alpha equals 1 or 2 will tell us whether we are dealing with row x or pi x. And these guys, we're just going to write them like this and pi like that. So these are going to be the coordinates. The row x's are going to be the coordinates on the statistical manifold, on the simplex, and the pi x's are going to be the coordinates on the cotangent space. And you can see now what the difference is with before. Before we have the probabilities of I and the corresponding momenta, right? So the way this is actually going to work is that whenever we had an I before, and it is discrete, I goes 1, 2, 3 to n, to little n, now we're going to have a continuous index. Whenever you had a summation, now this is going to become an integration. To give you a flavor of how this works, consider a vector. Let me show you what a vector looked like before. A vector in the finite space was something that looked like d theta I. These are the components of the vector, and then these are the basis vectors. and I am summing over I. Now, in the continuous case, a vector is still a curve on this funny space, and it's parameterized by lambda. And so now what we're going to have is the rho x d lambda, and then the basis vector is going to be the rho x plus d pi x d lambda, and the basis vector is this functional derivative by x. And we can either use the convention of summing over the repeated indices, but now, or we can just say, well, summation of the repeated indices now means you take an integration. Similarly, our gradient the gradient of a functional is going to be given by, you take the derivative with respect to the coordinate, and then the coordinate with respect to lambda, plus derivative with respect to the other coordinate, and then coordinate with respect to lambda, and implicit here is an integration. So this looks exactly the same as before. The gradient of f, this is a covector, can be written as, take the components, the same that appeared up here, and then the gradient of the coordinates. And of course, implicit in all of this is an integration. There is two quick remarks, and the first remark is that the reason I'm using tildes for these gradients in these spaces is to distinguish the gradient on this cotangent bundle, to distinguish it from the gradient of a function, which typically is just something like that. So the gradient in the configuration space is something like this. No tildes. The gradient on the cotangent bundle, I put the tilde to show what are the variables that are that we're differentiating with respect to. There is another thing that maybe I should have reminded you earlier. Sorry about that. Of course, this is the kind of thing that most of you have probably been exposed to, which is all this business of functional derivatives that are appearing all over the place in this. Okay, so just a remark. What is the clever way to think about functional derivatives? Here it goes. Functional derivatives are partial derivatives on steroids. What do I mean by that? Suppose that you have a function f. How do you define the partial derivative of the function f? Okay, x has many dimensions. So the typical way is you say you change x1, keeping x2, x3, and so on, all fixed. Very good. That's perfectly fine. That's the way we define partial derivatives. But you probably realize that when you're doing functional derivatives and you have infinite dimensions, like what you have here or there, right? And you have infinite dimensions, to vary one coordinate, rho at the point x, while keeping all the others fixed, is actually pretty difficult to handle because these other coordinates are sort of like infinitesimally near, right? And so how do we handle these functional derivatives efficiently? The way I think about it typically is, well, let's look at what partial derivatives are. One way to define partial derivatives is to say, if I were to consider a small change of the function, the small change of the function comes about from doing derivatives of the function and multiplying by small changes of the coordinates. So figure out how much the function changes when you change the coordinate, multiply by the coordinate, and then add them all up. And so what are the partial derivatives? Partial derivatives are the coefficients of the changes of the variables. That's what partial derivatives are. Functional derivatives, let me do functional derivatives with respect to rho, are exactly the same. We're going to figure out how the functional f varies, changes, when you change rho. So now we're going to say, well, imagine that you have a small change in rho. The coefficient of that small change is what we're going to call the functional derivative. And the big difference is that we have to add over all variables here. We have to add over all variables, then we integrate over all variables. Here we add over all indices. Here we add over all indices. The index happens to be continuous, so this gets transformed into an integration. So this is the best way to handle functional derivatives effectively. Just have your f, figure out a small change rho, and whatever appears as a coefficient, that's your functional derivative. Having said that, let's proceed with our notation. Here you see, here we have our vectors as being summations of these components and basis vectors and all of that. It might be much better, a much better idea to introduce an index notation. We're going to talk about a point x on the cotangent space, and we're going to assign indices to these guys, alpha x. And what these guys are going to be, this is going to be value 1 and value 2 for the alpha, and the 1 is going to represent the x, the rho, and the 2 is going to represent the pi. So alpha here takes two values. One is rho and the other one is pi, and then x takes an infinite number of values, continuous infinite. And so with this notation, vector is going to have components alpha x, and then these are the basis vectors. And the way this is actually being organized is that the alphas involve a sum, alpha 1, 2, and the x's involve an integration. So it's just exactly the same up-down notation that we've seen before, except that now these guys x's involve an integration. And what that expression means is exactly the integral that appears here. This is v1x, and this is v2x. We can write it like as a vector d rho x d lambda d pi x d lambda. Very good. The gradient, the directional derivative, is the gradient of f, the covector acting on the vector v. And this is what we are going to write as df dx alpha x multiplied by v alpha x summed over alpha summed over x. And that expression is exactly the one that appears here. The summation over x is an integral. At first, it's sort of weird to say, okay, what's going on here? Then you get used, and there is a great relief in not having to write those integrations all over the place. Very good. So now we're ready to write. Now that we have this notation, we are ready to write our symplectic form. Now, this is highly non-trivial. Recall, when we were doing the cotangent bundle, in the case of the embedded, of this embedding space for the simplex, the points x that we called alpha I, we used as coordinates the probabilities and then some coordinates on the cotangent spaces, these pi's. And the big question that arose then was that we have no idea what these are. When you have the cotangent space, you pick some axis here, and then you're going to have pi 1, pi 2, pi 3, all the way to pi sub n, right? But which are the pi's that you pick? Which is the pi that turns out to be conjugate to the thetas? In that sense, just given a raw cotangent bundle, there is no natural symplectic form. You have to pick which is the pi that goes with a particular theta. In classical mechanics, we do assign a symplectic form by saying, look, you have coordinates and you have momenta. Where do the momenta come from? Well, the momenta come from the fact that you have a Lagrangian and you pick the momentum, define the momentum in terms of the Lagrangian by taking the partial derivative of the Lagrangian with respect to q dot. So this is how we pick the momentum in classical mechanics. The lingo is that in classical mechanics there is a natural symplectic form. How does that come about? Well, if you have a Lagrangian, then there is a unique or rather a natural choice of what the momentum is going to be, and from this you proceed to invent your symplectic forms. You introduce the momenta as canonically conjugate to the coordinates, and so on and so forth. The problem in entropic dynamics, there is no Lagrangian to define what the momentum is. So how do we proceed? Well, but we do have that dt rho is given by that functional derivative that we had before. So in entropic dynamics, there is no Lagrangian. The role of the Lagrangian in defining what is going to be the momentum conjugate to the coordinates, the momentum conjugate to the coordinates, is given by the continuity equation. Is given by entropic updating of the probabilities. This suggests that we're going to choose phi as being the momentum. The natural choice of symplectic form of momentum that is canonically conjugate to the coordinates, to the probabilities, is given by the equation of evolution of probabilities in entropic dynamics. Very good. Now, once we have that, we're halfway there. We'll say, therefore, we're going to invent our symplectic form as being the gradient of rho and the gradient of phi. This is where the momentum comes in, minus, this is an antisymmetric tensor, the gradient of phi, gradient of rho. And this guy obviously has two slots for vectors, because there is one slot here for a vector, another slot there for a vector. And if here we were to put two vectors, v, u, then we have that omega of v, u, is going to be given by the gradient of rho acting on v, the gradient of phi acting on v, that's the first slot. The gradient of phi here acts on the second, the gradient of rho there acts on the second. And when that happens, of course here you may want to include an integration. Since one is up, the other one down, the integration is kind of implicit, but we can write it down explicitly. And when you do that, then this guy, the gradient rho acting on v, gives you the first coordinate, first component. This guy acting on the second one gives you the second component, minus the second component, u first component. And if we write this in components form, we may want to write this with indices. So this is going to be alpha x beta x prime v alpha x u beta x prime. And so here you have again, I'm summing over the alphas, summing over the betas, integrating over x, integrating over x prime, and this gives the form of our symplectic, the components. A symplectic form is going to have a standard form with deltas, where previously we had a Kronecker delta, now we have a Dirac delta. Very good. Next step, if you want to impose the preservation of this symplectic form, we are interested in flows that preserve the symplectic form. This leads to the following flows. The idea is exactly the same we had before, except that now we have continuous indexes. Instead of summations, we have integrations. Instead of partial derivatives, we have functional derivatives. And V here is some Hamiltonian function. D phi x, the lambda is minus the derivative of this Hamiltonian function, d rho x. So it's exactly the same thing as we had before. The symplectic form applied to two vectors turns out to be equivalent or the same as the Poisson brackets of the corresponding Hamiltonian functions, where the Poisson bracket of two functions is obtained by taking the derivative of the first with respect to the coordinate, derivative of the second with respect to the momentum, minus, do it the opposite way, u tilde d rho x, and now we sum over all the indices. We just integrate there. So you see the mathematical formalism is exactly the same. We have obtained Hamiltonian flows. So these are Hamiltonian flows. Very good. Time to stop here. In the next segment, we're going to impose that the metrics also be conserved. See you then.